Now, I will explain about Kepler's law of planetary motions. So, there are three fundamental principles that describe the motions of planets around the Sun. The first law, known as the law of ellipse, which stated that every planet moves in an elliptical orbit with the Sun located at one of the two foci of the ellipse. This law explains that planetary orbits are not perfectly circular, but have varying distance from the Sun throughout their motions. The second law, also called the law of equal areas, stated that a line joining a planet and the Sun sweeps out equal areas in equal intervals of time. This means that a planet travels faster when it's closer to the Sun and slower when it is farther away, while conserving its angular momentum. Kepler's third law, also known as the Harmonic law, which describes the relationship between the orbital period of a planet and size of its orbit around the Sun. The law stated that the square of the orbital period is directly proportional to the cube of the semi-major axis of the elliptical orbit. This means that planets with larger orbits require a longer time to complete one revolution around the Sun than planets with smaller orbits. By combining Newton's gravitational law with the principles of circular and elliptical motions, the proportional relationship can be written as t squared is equal to 4 pi squared times a squared divided by gm, where g is the universal gravitational constant, m is the mass of the central body, and a is the semi-major axis of the orbit. This equation provides an exact mathematical relationship that allows the orbital period of planets, moons, and artificial satellites to be calculated accurately.
Now, let's look at the application of Kepler's law of planetary motion. The first application is satellite orbit design. Kepler's law helps engineers calculate the orbital path, speed, and orbital period of satellites around the Earth. This ensures that satellites remain in stable orbit and function efficiently. For example, GPS satellites are placed in medium Earth orbit to provide accurate positioning and navigation service around the world. The second application is space exploration and mission planning. Scientists use Kepler's law to calculate the best trajectory, travel time, and fuel requirement for spacecraft traveling between planets. This allows space missions to reach their destination safely and efficiently. A good example is NASA Perseverance rover mission to Mars, which relied on orbital calculation based on Kepler's law. The third application is predicting planetary motion. Astronomers use Kepler's law to predict the position, speed, and orbital period of planets, comets, and asteroids. This prediction improves the accuracy of astronomical observations. For example, the return of Halley's comet can be predicted because its orbit follows Kepler's law. Next, let's look at 3 daily life applications of Kepler's law of planetary motion. The first application is GPS navigation. GPS satellites orbit the Earth based on Kepler's law, allowing their position to be predicted accurately. This helps navigation system provide precise location and direction. For example, Google Maps uses GPS satellite signal to guide users to their destination. The second application is weather forecasting. Weather satellites follow stable orbit calculated using Kepler's law. They monitor clouds, storms, and rainfall to help meteorologists predict weather conditions. For example, the Himawari 9 satellite provides real-time weather image for forecasting. The third application is communication technology. Communication satellites remain in stable orbits using Kepler's law to transmit television, internet, and phone signal. For example, Malaysia's near-sat 3D satellites provide reliable communication services across the country. In conclusion, Kepler's law is important because it supports many technologies that improve our daily life.
The next part, we move to the problem solving. This figure shows Kepler's law of planetary motion. The planets with mass m move around the Sun with mass capital letter of M in an elliptical orbit. According to Kepler's first law, the Sun is located at one focus of the ellipse while the other focus is empty. The symbol A represents the semi-major axis, which is the average distance between the planet and the Sun. The full length of the major axis is 2a. The arrow indicates the direction of the planet's motion, and T represents the orbital period, which is the time taken for one complete revolution. At the bottom, Kepler's third law is shown as T square is equal 4 pi square over gma cube. This equation means that the square of the orbital period is proportional to the cube of semi-major axis. Therefore, planets that are further from the Sun take a longer time to complete one orbit than planets closer to the Sun.
In this example, I will show how Kepler's second law can be used to derive the law of harmonics, which also known as Kepler's third law of planetary motions. Our objective is to prove the following equation, which is T square is equal to 4 pi square a cube divided by g and m, where T is the orbital period, A is the semi-major axis of the elliptical orbit, G is the universal gravitational constants, and also m is the mass of the central body. We are also given the Kepler's second law, which stated that a planet sweeps out equal areas in equal interval of times. This means the area of velocity remains constant throughout the orbit. Mathematically, this law is written as A dot is equal to L divided by 2m, where L is the angular momentum of the planet and m is the planet's mass. Now, I will explain how to prove these equations step by step. Step 1, we have to calculate the areas of the ellipse. The total area of an ellipse is given by A equals to pi times A and B, where A is semi-major axis and B is the semi-minor axis. For the step 2, since the planet sweeps the entire area in one orbital period, T, the area velocity can also be written as A dot is equal to A divided by T. Then we can substitute the area of ellipse from step 1 into A. So it will become A dot is equal to pi times A and B divided by T. Now we have two expressions for the area velocity, which are A dot is equal to L divided by 2m and A dot is equal to pi times A and B divided by T.
In step 3, we equate the area velocity with Kepler's second law. By substituting the area of the ellipse into the equation, we obtain the expression T equals 2 pi ABM divided by L. Then, we square both sides and get the expression T squared equals 4 pi squared A squared B squared M squared divided by L squared. Next, we substitute the angular momentum equation. L squared equals gm m squared a times 1 minus e squared, and the relationship b squared equals a squared times 1 minus e squared. After cancelling the common terms, the equation becomes much simpler. Finally, we obtain Kepler's third law, which states that t squared equals 4 pi squared over gm times a cube. This means that the square of the orbital period is proportional to the cube of the semi-major axis. Therefore, planets that are further from the Sun take a longer time to complete one orbit.
For subtopic 5.5, the law of harmony, for introduction, Kepler's third law, also known as the harmonic law, describes the relationship between the orbital period of a planet and the size of its orbital around the Sun. It states that the square of a planet orbital period is directly proportional to the cube of the semi-major axis of its elliptical orbit. The law is derived from Kepler's second law, which states that a planet shifts out equal areas in equal interval of time. The constant variability is given by A dot equal to L over 2m equal to L over 2, where uppercase L is the angular momentum, m is the mass of the planet, and lowercase l is the angular momentum per unit mass. Integrating over one complete orbit gives T equal to 2a over L, where A is the area enclosed by elliptical orbit. Since the area of an ellipse is A equal to pi AB, and using the relation B equal to A square root of A minus E square together with L square equal to GMA times A minus E square. The equation becomes T square equal to 4 pi square over GM times A cube. This equation shows that the orbital period depends only on the semi-major axis of the orbit and the mass of the central body, making Kepler's third law one of the fundamental principles of celestial mechanics. Application of law. Determining orbital period. Because the law is used to calculate the time required for a planet or satellite to complete one orbit around a central body. Studying planetary systems, astronomers use the law to compare the orbital characteristics of planets in the solar system and discover exoplanets orbiting distant stars. Understanding celestial motion. It explains the relationship between orbital distance and orbital period, providing a foundation for celestial mechanics and gravitational studies. Example, if you look at the figure below, the line around the Earth is low Earth's orbit, and above the Earth is satellite. Given Earth mass m equal to 5.97 times 10 power of 24 kg. Earth's radius r equal to 6.37 times 10 power of 6 meter. Satellite altitude h equal to 400 km. Using the formula below, the orbital period is t equal to 92 minutes. From here, we can get a low Earth orbit satellite revelation by using formula total time in one day over orbital period, which is 15 to 19 revolutions around Earth each day.
Next, I will present about the application of daily life using the harmonic motions law. The first application is satellite for Earth observation. Kepler's third law helps scientists calculate the orbital period of satellites, allowing them to travel in the correct orbit around Earth. This is very important for satellites used in agriculture, mapping, and environmental monitoring. By following a predictable orbit, satellite can pass over the same location regularly to collect accurate image and data. For example, Google Earth using satellite image to create detailed maps. Environmental agencies also rely on satellite data to monitor deforestation, observe forest change, assess crop health, and detect natural disasters such as flood and wildfire. This application helps governments and research make better decisions to protect people and the environment. For the second application is astronomy and scientific research. Astronomers use Kepler's third law to calculate the orbital periods and distance of planets, moons, and exoplanets that orbit distant stars. By studying these orbital motions, scientists can predict the movement of celestial bodies and gain a better understanding of how planetary systems are formed and evolve. In conclusion, Kepler's law is not only important in physics, but it also plays a vital role in satellite technology, environmental monitoring, and space exploration. For example, based on the question above, these are the step by step to solve the solution by using Kepler's harmonic laws, also known as Kepler's third law, is derived using the Newton's second law. For step 1, we need to writing the two equations. First equation is the gravitational force is Fg equals to Gm mass multiply mass over r square. Then the next equation is centripetal force need for circular motion. Formula is Fc equals to mv square over r. Since gravity provides the centripetal force, we set these two equations equal. Next, for the step 2, we cancel the mass of the orbiting object m from both sides. This gives us v square equals to gm over r. For the step 3, we use the equation for orbital speed. Since one complete orbit is the circumference of a circle, the distance traveled is 2 pi r. Therefore, it will be v equals to 2 pi r over t, capital T, uppercase. Actually, the t is the orbital period. Step 4, securing both sides give. So it will become v square equals to 4 pi square r square over t square. Step 5, we substitute this expression for v square into the previous equation, giving become to 4 pi square r square over t square equals to gm over r. Finally, for the step 6, we arrange the equation to obtain t become t square equals to 4 pi square over gm r square r the power of r power of 3. I'm sorry. Since G and M are constant for the same central body, we conclude that become the of Kepler harmonic law formula, which state that the square of planet's orbital period is proportional to the cube of its orbital radius. For the diagram based on the question and the solutions, on the left side is a circular orbit. In this case, the orbiting body labeled as small m moves around the central body big M in a perfect circle with a constant radius r, represented by r. The green arrow represents the velocity of the orbiting body, which is always tangent to the circular path. Meanwhile, the blue arrow represents the gravitational force, which always points towards the central body. This inward force acts as the centripetal force that keeps the object moving in a circular orbit. On the right side is the elliptical orbit, which is the more general case. Unlike the circular orbit, the central body is located at one of the two foci of the ellipse, not at the center, because this is the distance r between the orbiting body and the central body change continuously as the object moves along its orbit. The longest diameter of the ellipse is called the major surface, and half of this distance is known as the semi-major axis, represented by A. The semi-major axis is an important parameter because it determines the size of the orbits and is commonly used in orbital mechanics calculations. For the overall, from these two circular and elliptical orbits are governed by gravitational force. A circular orbit has a constant radius and constant orbital speed. Meanwhile, an elliptical orbit has a varying distance from the central body, causing the object speed to change throughout its motions according to Kepler's law.
In conclusion, Kepler's third law explains the relationship between how long a celestial object takes to complete one orbit and its distance from the central body. It shows that objects farther away from the Sun take a longer time to orbit compared to those that are closer. This principle is derived from gravitational force and motion in space, and it plays an important role in understanding how planets and satellites move. It is widely used in astronomy to study planetary systems, predict orbital behavior, and analyze satellite movements such as those in low Earth orbit.